after we have a chemical reaction, a metathesis reaction, where we watch this pattern here, where we have AB, CD. AB is an aqueous ionic compound. CD is also an aqueous ionic compound. And it comes together in a different combination. So AD forms, maybe it's a solid. CB forms. How did I know C was going to be first here?
I memorized it.
No, you didn't memorize it. C goes first because it's a cation, right? This is an cation, anion, cation, anion. We always put the cations first. So in this metathesis reaction, what we have here is we have ions dissociating. From this, we form an ionic compound, ionic reaction, right? Whoops, there we go. C plus, D minus. Those aren't fun things to hear, huh?
Yeah, I want a D minus.
Okay, and then AD stays together, solid, and C plus and B minus dissociates as well. So that's our general pattern for our equation, and then this is our ionic equation. And now if we cross out the spectator ions, we see the things that on the left haven't changed from going to the right. In this case, it would be C plus and B minus. Haven't changed. The A and the D have come together, form a compound here. So we can identify the spectator ions to create what we call the net ionic equation. So here's some reactions. Easy part here. You guys are just going to pick out the spectator ions and rewrite the net ionic equation. All right? Push pause, go over these three, and then Fred will help us out. All right, go for it, Fred. What are the net ionic, or what are the spectator ions here?
The nitrate hasn't changed and the potassium ion hasn't changed.
Very good. So the potassium ion and the nitrate ions are gone, and then we just write what's left over for our net ionic equation. Okay, if you didn't get that one, push pause and try it again. So what are our spectator ions here, Fred?
Sodium ion and the chloride ion.
All right, sodium ion and the chloride ion don't change. How about for this last one here?
Sodium ion and the nitrate ion.
Very good. Sodium ion and the nitrate ion. Okay, excellent stuff. All right. Now, we have talked about acids being molecular compounds that dissociate when placed into water. We also talked about how acids start off with hydrogen. So, for example, HCl dissociates when placed into water, into the hydrogen ion and the chloride ion. There's another way to write this that some chemists like to use, and so you have to become familiar with it. This is where we say that HCl interacts with a water molecule, and that the water molecule, I'm going to draw this out, here's the water molecule, it takes one of those hydrogen ion, or it takes the hydrogen ion from the HCl, the hydrochloric acid there, or hydrogen chloride, and forms an H3O plus ion. This is called the hydronium ion. This species has a positive charge, and the result here is the chloride ion. So water molecule here, a water molecule, will take a hydrogen ion and grab onto it. Okay? Now, this is just another way to kind of depict what's going on here. I personally am not a huge fan of this because it kind of, there's a reason why they do it, and it's a little bit more involved, but anytime you see anything that's ionic or molecular, and it's the case of an acid, HCl, and it says aqueous, we have to be aware now that if we see something that's ionic, so for example, sodium chloride, or something like an acid that says aqueous, if it says aqueous and it says aqueous, what does that tell us, Fred?
Know that those compounds are ionized.
That's right. Those compounds dissociate into their ions, right?
Yeah, that they're ions.
That's right. There's no sodium chloride in this scenario. It's just sodium ions and chloride ions, and they are aqueous. to be aqueous means not just dissolved in water, where it is, that's exactly what it means, but it also means in the case of ions, if I draw this and say this is a sodium ion aqueous, what that means is there's a sodium ion, it's positively charged. I'm going to draw a little sphere around, a circle around it, it's a spherical entity. And the water molecules are surrounding this in such a way that the oxygen ends of the water molecules are huddled around this sodium. So lots of water molecules, not just as many as I could draw here, but maybe even hundreds, thousands, are gathered around this sodium ion, providing electron density for that positive charge and stabilizing it. For the chloride ion, for example, what this means is, if somebody writes the chloride ion, what they really mean is a spherical entity with hydrogen ions or hydrogen atoms from oxygen molecules accepting that negative electron charge onto themselves because the hydrogens are electron poor in water molecules. So the hydrogen ends are surrounding that chloride ion and stabilizing that negative charge. Okay? If we look at this in the terms of an acid, something like HBr, aqueous, if you see something like that, what that means is the hydrogen ion is associated with water molecules, right? So oxygen from a water molecule will grab onto that hydrogen ion. Now that hydrogen ion doesn't stay there very long at all. As soon as it comes on, the other one feels unwelcome. One of the other ones will feel unwelcome and leave. And they'll go to a different water molecule and form a new bond. Electron density will come over here and grab onto that proton. And this new water molecule on the right here now, will become the hydronium ion and have a positive charge associated with it, while this one here will be our leftover water molecule. But that doesn't happen long either, because right after that, another water molecule.
I know what's going to happen.
What's going to happen?
That water molecule is going to get the hydrogen.
That's right. The electrons from here are going to reach out and grab onto that hydrogen again, and the process is going to continue over and over and over. In fact, the hydrogen isn't in one spot with a water molecule. It's bouncing all over the place, and it's not the same hydrogen ion either. If I have a solution of water with some hydrogen ions free in it, some acid in it, the location of the acid is something that you can identify because it's bouncing all over and it can spread like electricity down a wire, right? The electrons jump onto this end of the wire and other electrons jump off the other end. They don't pass through as fast as the light will turn on right when you flip the switch, right? And the same thing is true with hydrogen ions within a solution of water, for example. So because the hydrogen ion doesn't take more than one water molecule at a time, so to speak, I mean, people will write this HCl with just a single water molecule and show an acid dissociating with water to form the H3O plus and the chloride ion. This is also a helpful model when talking about weak acids and weak bases, or specifically weak bases, and we'll get into that in a bit. But an acid can be defined then as a compound that when placed in water, the hydrogen ion results, or the hydronium ion results. Another way to say this is you put an acid in water and a proton is donated to something else. All right? In this case, the proton is donating to a water molecule. All right? And when people want to stick with that definition that a proton is donating to something else, that's what an acid is, something that donates a proton to something else, then they'll need the water molecule to have it donating it to there. Your definition of an acid can be that it donates a proton to something, but it's more flexible to think of an acid as something that just puts protons into solution. And if there's something to absorb them, it will. Otherwise, water molecules will just kind of entertain that proton for as long as they need to. This compound here is an acid. You know how to name acids, Fred.
Well, I did it once. I'm not sure if I remember.
This is not a binary acid like hydrochloric acid. This is oxoacid. Do you recognize this polyatomic ion here?
Let me look at the chart. Oh, that's the acetate ion.
Okay, that's the acetate ion. Good. So the acetate ion, 8, ends in 8. What would its acid be?
8 goes to ic. Acetic acid?
Acetic acid. Very good. Acetic acid. Acetate, 8 goes to ic. Acetic acid is a weak acid. Now, weak acids, when you put them into water, they donate a hydrogen ion to water, or you could say they result in the hydrogen ion when placed into water. But that hydrogen ion doesn't leave the acetate ion for very long. As soon as it separates, the acetate ion feels a little unstable and will pull a proton off of a different water molecule, and it'll go right back here. All right? And the result is some hydrogen ion always floating around, but the acetate ion isn't completely stable, and it'll grab a proton and go back. And in a strong acid, like HCl, when it's placed into water, it completely dissociates. But a weak acid, like acetic acid, it will only dissociate for an amount of time, or in other words, there's only a relatively small number of them dissociated at any one given moment. And that's what makes it what we call a weak acid. Okay? Now on your back of your periodic table, we have a list of the strong and weak acids. And that's nice of me to give you. But I want you to work hard to begin to recognize these acids as our strong acids. You will need to know your strong acids by the end of the semester. Now the chart will be there to help you, but I need you to use those frequently. Anytime you see an acid and you're asked, is this a strong acid, or you have to make a decision about whether it's a strong acid, you need to go to your chart and begin to recognize which ones are strong acids. Okay. That's a good place to stop. Next time we'll talk about these bases.